So now that we have our graph in place, let's see what we can do with it. So we've got a couple of nodes here. Let's find the shortest path between these two nodes, and it tells us the shortest path goes through these kind of things. Remember, our paths don't have any weights, so we're not interested in Dijkstra path at this point. And we can look at this path. It tells us that the path length between these two nodes is 5, right? So if we can check that out, we could say, get rid of the path length here, shortest path, and that tells us it's 1, 2, 3, 4, 5. That's our path length here, from 167,099 to 15 to 65,803 to 976. You can get from that node to that. Then the next thing we want to do is look at the number of connected components in our graph. What are the connected component? It's if you look at our graph over here, there's no way to get from 352018 to 16523. Because these three nodes, the three nodes in this left bottom corner of the graph, are not connected to any of the nodes that are in the rest of the graph. So these three nodes form what's called a connected component, because you can go to nodes within that component, but you can't go to nodes outside that component. And looking at our graph visually, we can see that there are two connected components. One is this huge little thing in the that dominates it, and then there's a little 3-node set that's outside it. So that's our connected components, but we can see that in our graph. But in general, we want our graph, we want to be able to find it, because graphs, for example, in the entire 366,000 node graph, you probably won't be able to see it. So we want to find out how many connected components we have. So there's a function called connected components that will tell us will give us the connected components of the graph itself, right? So we can print those. So this tells us our connected components. This is the function that we're looking at. And what it does is it returns a list of connected components, and we are printing each one of them, sets of connected components, and it tells us that we have one connected component that contains all these nodes, and a second connected component that contains these 3 nodes, right? So that's what we have here, right? And this is kind of important, because if you're looking at communication across nodes in the graph, then we know that in our graph we can't send a communication from one node to every other node in the graph, because if you start with, let's say, 30177, we're not going to be able to get to 353216. The message will never get there, right? That's the goal of finding connected components. So ideally, of course, in a perfectly communicatable graph, you would have only one connected component, but ours has 2. So let's just separate these out into 2 components. So we have a largest component, which contains the most number of elements. That's this one. And the smallest component that contains the 3-graph network here. It's kind of nice. They're all fully connected. So that's kind of nice. We have the graph. We can look at the degrees in the graph. So we could do nx.degree, and it tells us, in this case, the degree will really tell us how many friends a particular node has, right? So we have 206 friends for one, 155 for 2, etc. So that might be useful in a social network to find out how many friends someone has, who has a lot of friends, who has a few friends. And we could look for the max degree to see the friend with the most number of users, and it tells us that node number 1 with 206 friends has the highest degree there. So degree, of course, is just a simple function, and we can use the Python max function and tell it use that to actually get the maximum. So degree is coming back as a dictionary. The key is the node number, like for example here, and the value is the number of friends. So we want to tell it that we want to get the value, because we are interested in finding the max using this, not using the key, but using the value, right? So this tells us degrees.get is actually going to get us the value here, this one, and we're saying use that to find the maximum. Okay. That's what this is doing here.